So the last few classes we've been discussing energy, which is a incredibly important topic in physics, in chemistry, in engineering, and beyond. We talked about the concept or the idea of energy. We talked about the fact that forces transfer, exchange energy. We talked about the fact that energy is conserved, is never created or destroyed. And we looked at a number of illustrations of energy and energy conservation and energy transfer, looked at a number of example problems of energy, energy conservation, and energy transfer. So today's class, we move on to a different but related topic. So we're moving on from energy to momentum. And like energy is a very important concept or idea in physics, momentum is also a very important concept or idea in physics. And in some ways they're similar, we'll see. In some other ways they're different. We'll see that too. So we're going to talk about the idea of momentum, concept of momentum. We're going to talk about like forces transfer energy. They also transfer momentum. We'll talk about that like energy is conserved, never created, never destroyed. Momentum is conserved, it's never created, never destroyed. And we're going to look at examples and illustrations of momentum in a similar way to we looked at examples and illustrations of energy. So that's basically the plan, and that's today's class, and it's Thursday's class also. And I just wanted to stress this, and so Lady Gaga's come to class again when there's something very important in a particular class. There's something important in this class, and what's important is, you know, this huge role, this key role that energy momentum, and especially energy momentum conservation, play in science. We'll see that they give us a much deeper understanding, a much deeper explanation of how things work. And they give us new tools, new methods for solving physics problems. And so that's the power, that's the usefulness of energy and momentum conservation. Okay, so we're going to learn, kind of like we learned how to see energy and work in the last few classes, we're going to learn how to see what we call momentum and impulse. So I'm going to go on now and introduce momentum and impulse like we introduced energy and work before. And we'll start to get familiar with these new concepts. We'll start to get used to these new ideas. Okay, so let's define momentum, and let's also define impulse. So we use momentum in our everyday language, and we use sometimes impulse in our everyday language. And in sort of everyday language, the way I think of momentum is that momentum is, if something has large momentum, it's very hard to stop that something. So a truck, fast-moving truck, has a large momentum. It's hard to stop that fast-moving truck. A fast-moving elephant, right? That has lots of momentum. It's hard to stop that fast-moving element. On the other hand, right, a fly, it's relatively easy to stop a moving fly. A beetle, right? It's relatively easy to stop a moving beetle. They have the moving fly. The moving beetle have small amounts of momentum. And so in everyday language, sort of a gauge of whether something's large momentum or small momentum is whether it's easy to stop or hard to stop. In physics, on the other hand, we're a bit more specific, we're a bit more concrete, we're a bit more quantitative about the definition of momentum. And so in physics, momentum is specifically defined here. We give it the symbol P. I don't have any idea why we gave it the symbol P, but that's the symbol for momentum. And it's equal to, is defined as, it means simply the mass times the velocity of an object. So an elephant has momentum, which is the product of the elephant's mass and the elephant's velocity. A truck has momentum, which is the product of the truck's mass and the truck's velocity. Impulse is what we call change in momentum. So impulse, we give the symbol delta P, change in momentum, and the impulse that's given to an object, a body or particle, is its mass times its change in velocity. So, when you have an object, maybe it is an elephant, maybe it is a truck, maybe it is a fly or a beetle, and it changes its velocity, it also changes its momentum. And that change in momentum is what we call impulse. Like we called work a transfer, a change in energy. And so here's the equation for impulse. The product of the mass of the object times the change in velocity of the object. Let me make a couple of remarks about these two definitions that I've introduced. Firstly, units or dimensions. So we can, this is a new quantity, momentum impulse. We can figure the units of the new quantity by thinking of the equations that define the new quantity. So momentum and impulse are going to have the same units, because one's momentum and one's change in momentum. And their units are the units of mass, which we know is a fundamental unit, kilograms, and multiplied by the units of velocity or change in velocity, which is velocity is made out of meters and seconds, meters per second. So that product is the units of momentum. You can write the units of momentum as kilograms, meters per second, or you can write it, we often do this, there's another way of writing it with a Newton. It's Newton, comes out to be Newton seconds. So that's one remark about momentum and impulse. A second remark is that, and this is where momentum and energy are different, and where they're kind of interestingly different, that has some interesting consequences. Momentum and impulse are vectors. Energy and work were scalars. So the energy of something or the work done on something is just a number. The momentum of something, the impulse given to something, is both has a magnitude, a size, and it has an orientation or direction. So that is a very important, very fundamental difference between our concepts of momentum, our concepts of energy, and also impulse and work. Okay, so significance of momentum and impulse. I want to show you the significance of momentum and impulse. And this story of the significance of momentum and impulse really starts with Newton's second law. So go back and, remember Newton's second law. Remember, it's F equals ma. Okay, my mom and dad know that it's F equals ma. We all know that Newton's second law is F equals ma. Let's just revisit it. And I'm going to revisit it in this way of writing it. So it relates the force that's acting on something. So over here on the left is the force to the acceleration or the change in velocity of something. Over here is the acceleration written in terms of the velocity change and the time interval. And so that's the way we've been writing Newton's second law up to now. Now I'm going to suddenly start calling that version 1.0 because I'm going to introduce a new version for Newton's second law. So what I'm going to do is snake the mass sitting outside here in the top equation that multiplies the acceleration. I'm going to sneak it up and multiply directly the velocity. So that's all I've done in the step from the first equation to the second equation. Let me get my pen going. I just moved this little guy here over to here. The reason I did that is to look at Newton's second law in a new way, a fresh way. Because now what Newton's second law says that the force determines the rate of change of the momentum. So this is momentum upstairs here in the numerator. This fraction is the rate of change of momentum in time. And so in terms of momentum, Newton's second law becomes really simple. Simply says that the rate of change of momentum is in proportion to the force, rather than that the product of mass and acceleration is equal to the force. And so these are just two different ways, version 1.0 and version 2.0, of looking at Newton's second law. One way you think about changes in velocity, and the other one where you think about changes in momentum. Now, the advantage of the change in velocity way of thinking about it is velocity is something we're used to, something we can see. The advantage of thinking about momentum and momentum change is that it's more closely, fundamentally connected to what forces do, what forces change. Okay, so that was introducing momentum and impulse and the relationship between momentum and impulse and forces. And it sort of resembles how we had introduced work and energy and a relationship between work and energy and forces. I want to go on now, like we did for energy, talking about energy conservation, to go on and talk about momentum conservation for momentum. So this is important. This is why it's useful. This is why it's handy. Let's think about this situation. And this is a situation that we've thought about in the past. It's an apple falling towards the earth. The apple, say, falling from a tree towards the earth. And so upstairs here is the apple, and downstairs here is the earth. And we now understand from all those classes up to this point that that apple falls with an acceleration of gravity, and it falls due to a force, a gravitational force between the earth and the apple. And what's particularly interesting is that the apple experiences a gravitational force downwards, but the earth is actually experiencing an equal-sized oppositely directed gravitational force upwards. And so that's our sort of force perspective, force picture on what's happening as the earth attracts the apple and the apple attracts the earth through gravity. And there's a very important thing about those pair of forces on the apple and on the earth is that they're equal and opposite. They're both exactly the same size, despite the fact that the earth is massive and the apple is light, but they're both exactly oppositely directed one another. Okay, so now I want to think about, well, what's going to happen? And I want to think about what's going to happen from the perspective of the motion and the velocity of the earth and the apple, and what's going to happen from the perspective of the momentum of the earth and the apple. So let's do that. And so over here on the left, I pictured right downstairs here. Oh gosh, didn't mean to do that. Well, that's fine. Right downstairs here, at the bottom, I've pictured version 1.0 of Newton's law, how forces relate to change in velocity. And so we're going to think about the change in velocity that's accomplished by these two gravitational forces that are experienced by the Earth and apple pair. For the apple, the change in velocity is relatively large. That's because it's light, and its velocity is easily changed by the gravitational force. For the Earth, its change in velocity, see this little velocity vector here, it's tiny. That's because it's extremely heavy, very massive. And so its change in velocity is small. And so if you stand back and watch this situation. Imagine this situation. You're seeing the apple fall towards the Earth. You see the apple moving, gaining velocity, but you can't see the Earth moving. And it's not because, the Earth is not moving. The Earth is fractionally moving, but it's only fractionally moving because it's so heavy, so massive. So from the perspective of changes in velocity, it seems like the apple's doing all the moving and the Earth is doing none of it. If you look from the perspective of momentum, so now we're going to use version 2.0 of Newton's second law, that forces change momentum. What do we see then? Well, in this case, if you look at this little law here, this version of the law, well, the apple gains some momentum. I pictured that change in momentum, that impulse over here on the top right, but the Earth also gains some momentum. Picture that as this arrow here on the bottom right, and those momenta that are gained, because the forces that are exerted are just equal and opposite. And so if instead of looking at the Earth-apple situation from the perspective of velocity, we could look at the Earth-apple perspective from the perspective of momentum, we would see not this unequal changes in velocity. We would see exactly equal and opposite changes in momentum. It would be kind of this sort of beautiful, symmetric situation as the Earth and the apple acquire equal and opposite momenta due to their interactions, their gravitational interactions with one another. And so that's all the consequence of this little guy here. Action and reaction, and Newton's third law, and the implications of action and reaction, and Newton's third law, that forces come in pairs, and our new interpretation that forces change momentum. Forces determine the rate of change of momentum. Okay, let's move on to the next slide. I gotta clear that. I gotta go to the next slide. Here we are. So I want to show you now how out of that last slide and that new perspective of momentum changes rather than the old perspective of velocity changes comes about momentum conservation. If you were to look from the perspective of velocity, and that's what I'm picturing over here on the left, then for sure velocity is not conserved, right? Initially, the apple in the tree and the Earth was stationary. The apple fell from the tree, now there's motion. And the motion of the Earth and the apple are not equal and opposite. And if you added up those velocities or those changes in velocities, there's some net motion. So that's not conserved. There's no conservation law for velocity. But if you think about momentum, you see that, oh gosh. If you look at momentum, you see there is a conservation law for momentum. And that's because, here it is. That's because, as we said, from the perspective of momentum, the change in momentum of the apple and the change in the momentum of the Earth due to the gravitational interaction between the Earth and the apple, they're equal and opposite. And so the apple's momentum, which is downwards in my picture, plus the Earth's momentum, which is upwards in my picture. These are two oppositely directed vectors of the same length. If you add them up, you get 0. And so momentum is conserved. Velocity was not conserved. And so that's a great virtue of thinking in terms of momentum. And doesn't come with the thinking of the action of forces in terms of velocity. If you think of the action of forces in terms of momentum, because of that third law, Newton's third law, because of action and reaction, the momentum, no matter what the forces do, the forces act to conserve momentum. They will never change the total momentum of the system. And so that's the great usefulness of momentum. Okay, I want to show you a demonstration of this. So I'm going to share a different screen. Okay, hope you can see this. Back in chemistry physics building in the large lecture room, and we're going to look at a little demonstration of momentum conservation. And let me start it going, and then I'll stop it and introduce it. Okay, what am I doing? That's a good question. What I've got is those two red cards. And you might remember these two cards because I can place the two cards together, and through a spring between the two cards, I can exert a force between the two cards, and that force is equal and opposite. It's a force pair. And we'll see that the card on the left experiences a force to the left, and when I release the spring, it will move to the left. The card on the right will experience a force towards the right. When I release the spring, and it will move towards the right. Now, the two cards are equal in masses. And so when I release that force, their velocity is going to change, but also now think about their momentum. Their momentum will change too. And we can think about that force as creating a change in momentum of the card on the left and the right. But because of momentum conservation, the total momentum of the cart on the left and the right, if you added their momentum vectors together, that would be 0. So I'm asking you to imagine this, right? This is an important thing to think about as you watch this video. Imagine as those carts fly apart, imagine their momentum vectors. Their sizes of the momentum vectors, the directions of the momentum vectors, and imagine how those momentum vectors would add together. And imagine the fact, well, you started with 0 total momentum of the two carts. Do those two momentum vectors after they're moving add together to make 0 total momentum after the action of the forces? So let's watch that. I'm going to put it in slow motion so we can see it nicely. Sounds like I'm in some sort of dungeon doing this, but it's actually the lecture room. Okay, so before I release the spring, before I release the force, both the card on the left and the card on the right were stationary. So there was 0 total momentum. When I released the spring, the car on the left had some momentum towards the left, the car on the right had some momentum towards the right. So both had momenta, but if you were picturing their momentum vectors, the momentum vector for the cart on the left plus the momentum vector for the cart on the right, because they're equal and opposite, will add together to make 0. So for the entire system of the two carts, there was 0 momentum before the force acted and 0 momentum after the force acted. Let me show you the case where I'm going to double the mass of one of the carts. And this time, watch both the carts' motion, think about both their velocity vectors and their momentum vectors. So now the cart on the right is twice the mass on the cart on the left. And so let's see what happens now when we exert the forces. Okay, so if you watch that situation from the perspective of sort of velocity perspective, then what you see is that the cart on the left is moving fast after the spring was released. The cart on the right is moving slow after the spring released. And so, you know, it's an example where there was no velocity to begin with, but there is net velocity after the spring was released. So velocity wasn't conserved. But if you watch that demonstration from the perspective of momentum, well, one of the carts, the one on the right, is twice as heavy as the other, or the one on the left is half as heavy as the other. So the one on the left is traveling fast, but has half the mass. The one on the right is traveling slow, but has twice the mass. Their momenta, which is the products of their masses and their velocity, they're actually equal in size, opposite in direction. And overall, the total momentum of the two carts is still 0. They start out with 0 momentum. They fly apart, one fast, one slow, one heavy, one light. The total momentum is still 0. So that's a nice example of momentum conservation. I got a second little video to show you. And this is called Newton's Cradle. And you might have seen this before. And it's also a nice demonstration, actually, of both energy and momentum conservation. But as we watch it, I'm going to talk just about the momentum conservation that's going on in this situation. Okay, so what you saw there was that I pulled one of the metal spheres, the one on the left, I pulled it further over to the left and released it. As it fell back towards the 5 other spheres, it's through the gravitational force, acquired some momentum. It strikes the other 5, and then the 5th one, the one on the far right, moves off towards the right. And that's how momentum conservation is taking place in this situation. I've given the ball on the left some momentum towards the right. It collides with the other balls, and then the one on the right picks up that momentum and conserves that momentum. Then there's a period in which the ball on the right swings up, swings back down. I won't talk about that, but as the ball on the right heads back towards the 5 balls on the left and strikes them, it gives up its momentum, comes the rest, and it gives the ball on the far left that momentum. And that ball on the left carries that momentum off. And that goes on and on and on, to and fro. A ball coming in from the left, giving the momentum to the ball on the right. The ball on the right coming in from the right, giving the momentum to the ball on the left. We can see it again now. I'm going to play this bit a little bit slower. If I pull two balls off to the left, so I double the mass, what's going to happen then? And so in this one, you see two balls come in the left, they strike the other four balls, and the two rightmost balls move off towards the right. Again, the momentum of the two balls coming in from the left is handed over to the two balls on the right. And then the two balls on the right swing back, hit the four balls on the left, and the two balls on the left swing off to the left. And so again, momentum is being transferred to and fro between the arrangement. And last of all, I'm going to pull three balls off towards the left, and we'll see the three balls on the right head on, and so on and so forth. The balls on the right striking the balls on the left and giving them their momentum, the balls on the left striking the balls on the right and giving them their momentum. And so this is a classic example, a beautiful example of momentum conservation. Okay. Let me go back to the slides, if I can do that. Okay, I wanted to make a remark about momentum conservation when you cannot apply it in the context of what we call external, internal forces. And on this slide, I've got two examples that indicate when you cannot apply momentum conservation and this idea of internal and external forces for what we call a system. So I'm going to start actually over here on the left-hand side and describe this situation, I think. So let me get the annotation going. It will only take me 10 minutes. Here we are. I'm starting over here. And I'm starting with this situation of an apple and the earth, and them being attracted by the gravitational force, the apple falling towards the earth falling towards the apple and the earth acquiring equal and opposite momenta. So here and here. If we thought of the apple on its own as the entire system, then we would not see momentum conserved because the apple is gaining more and more momentum. We have to think of the apple and the earth together, this green box, to see momentum conservation. If we think of the apple-earth system, then, well, the apple acquires momentum, the earth acquires momentum, the sum of the momenta are zero and momentum is conserved. So this is an important concept. If you were to just think of the apple here, then the Earth's force is a external force acting on the apple system. And if there's external forces acting on a system, then that system's momentum is not conserved. But if you think of the apple and the earth as a system, this entire arrangement, the force of the Earth on the apple and the apple on the Earth, they're within the system. There's now so-called internal forces. And because there's no other external forces, then the Earth-apple system's momentum is conserved. And so when you work with problems of momentum conservation, you need to work with the entire system, like the apple and the Earth. Momentum conservation can be applied when there's no external forces being applied to the system that would change the momentum. Momentum conservation only holds if you've just got the internal forces within the system that are changing the momentum of the components of the system, like the apple and the Earth. Another example would be if I slid a book across a desk. If I slide a book across a desk, right, and that's the right-hand side picture here. As the book, just imagine it. I mean, just do it for yourself, right? Take your physics textbook and slide it across the desk. You give it a nudge, start sliding, comes to rest. Well, if you're just thinking of the physics textbook, it looks like, oh my God, the physics textbook doesn't even conserve momentum. It started out with some momentum. I gave it a nudge, and then it lost it. It came to rest. That's because the physics textbook is being influenced by external forces, the force of the desk. If you included in the system the physics textbook and the Earth, right, that frictional force between the desktop and the physics textbook, that would no longer be an external force exerted by the desktop on the physics textbook, and it'd be an internal force in the physics textbook and Earth system. Then the momentum would be conserved if you thought of the total momentum of the physics textbook plus the Earth. So only when you think about the physics textbook plus the Earth would you see momentum conservation. The physics textbook's momentum changes, the Earth's momentum changes. Those changes are equal in size, opposite in direction, but added together, momentum would be conserved. So thinking only of the apple, thinking only of the textbook, momentum's not conserved because you got external influences, external forces. Thinking of the apple Earth system, the book Earth system, then momentum is conserved because those forces, gravitational forces or frictional forces, are internal to the system. So that's a very important idea, a very important concept that's important to think of when you're trying to apply momentum conservation. And it's easy to make mistakes when you try and apply momentum conservation because of jumbling up the external and internal forces. Okay, let's look at some examples. So here's my little dogs, Mimi and Baxter, running across the living room floor. And actually, Baxter's, I noticed, is even actually flying. There's no feet on the floor. So we're going to be asked the question about Baxter here. And the question is, well, we're told that Baxter has 40 joules of kinetic energy in this picture. And Baxter has 23 kilogram meters per second of momentum in this picture. And we got to find, well, here's an interesting question. I was wondering the other day, how heavy is Baxter now? He's been eating quite a lot. And so what's his mass? And in this picture, how fast is he running? So let's see if we can solve this. Knowing Baxter's kinetic energy, knowing Baxter's momentum, let's figure out those more familiar, more elementary perhaps quantities, that his speed and his mass. Okay, so here, of course, what did I do first of all? As you know, I always draw a picture. And so here's my picture of the situation. I've got, spherical Baxter here, and I've written down the information I know. It's got 40 joules of kinetic energy and 23 Newton seconds, or kilograms meters per second, of momentum. And we want to figure out his speed and his mass. And to do that, I'm going to begin with this information that we've been given. That is kinetic energy. That's the K here. Oops, sorry, I didn't mean to do that. This never quite works for me. Here's the kinetic energy. Here's how it's defined in terms of mass and velocity. And here's the 40 joules that we're told that Baxter has of kinetic energy. And then here's the momentum. Here's how it's defined in terms of mass and velocity. And here's the 23 Newton seconds of momentum that we're told Baxter has. And we're going to use those values and use how they're related to the masses and speeds to figure out Baxter's mass and speed. Now, this now has become, since I've written down these pair of equations that connect these fundamental quantities to mass and speed, this just becomes now a math problem, right? It's two equations with two unknowns. It's half mv squared equals 40, if you were a mathematician, and mv equals 23, if you're a mathematician. And I've got to solve those pair of equations for the two variables, the m and the v. So let's go ahead and do that. So solving for v, the way I solve for v is that I note, and look, there's a million ways of solving for v and m in this, I'm sure. I took 2 times the kinetic energy, which is mv squared, and divided by the momentum, which is mv, because I notice, right, if I do that, take 2 times the kinetic energy mv squared divided by the momentum mv, that just gives me v, the velocity or the speed. And so 2 times, oh my God, I need serious training with doing this that I'm not getting. Sorry. I'm having a panic attack right now, trying to get back to this thing. Here we are. So 2 times the kinetic energy, so that would be actually 80 joules, divided by the momentum, that's 23 Newton seconds, equals 3.7 meters per second. And so that's solved for the velocity. And then once I've solved for the velocity, then it's really easy. I could go to either of the equations above for the kinetic energy or the momentum. I could use either of them and solve for the mass. I use momentum equation. And if I rearrange that, the mass is just the momentum divided by the velocity. And so I just fed in the momentum divided by the velocity that I've now found and got Baxter's mass. And actually 6 kilograms. It wasn't that big after all. And so that's an example of definitions of kinetic energy and momentum and how they're related to those more everyday familiar quantities, mass and speed. Okay, let's clear that if I can. And let's go on. So this is really just a quiz question about the definitions of momentum energy in terms of the velocity of an object. In this case, the object's Baxter. So if you double the speed of Baxter, well, the momentum also doubles because it's in proportion to the speed. The kinetic energy, on the other hand, that quadruples. because it's in proportion to the square of the speed. If I tripled Baxter's speed, or if Baxter himself had tripled his speed, then his magnitude of the momentum would triple. The kinetic energy of Baxter would increase ninefold. So the kinetic energy and the momentum do depend on speed in a different way, and it's an important feature of kinetic energy and momentum. Okay, let's look at some more examples. So I actually know absolutely nothing about baseball. But that didn't actually stop me solving this problem. We're told that a baseball player has a mass of 85 kilograms and is running at 6.6 meters per second and slides into home plate, whatever home plate is. First question, what's the magnitude of the impulse delivered to the player by friction? And then second question, if the player's slide lasts 3/4 of a second, what's the average frictional force that's exerted on the player? So the player is sliding into home base, sliding from 6.6 meters per second, initial speed, to being at rest, final speed. So there's been a change in velocity, there's been a deceleration. That would be an old way of thinking about this problem. There's also been an impulse given to the player. The player's momentum has changed, and it's a force that gives an impulse to the player. And so we're going to approach this problem with these new ideas. We're going to figure the change in momentum of the player, that's the impulse, and thereby we're going to figure out the force exerted on the player, knowing the impulse. And so those are the steps in this problem. If you want to think about, supposing, I don't know anything about baseball, so how did I think about this problem? I thought about this problem as the book sliding across the desk. It starts out with my physics book sliding across the desk. Started out with some initial velocity, and it came to rest. It had some momentum. It lost it. There was a change in momentum. There was a change in momentum. There was an impulse given to the book, and that impulse was given by the frictional force between the book and the table. And so this problem of the baseball player sliding into home plate is the same problem as a physics textbook sliding across the desk. And we're going to figure out the impulse given and the force exerted due to friction. Okay, so of course I started with a sketch. I started with a picture. And I annotated the picture with the things I know. So on my sketch, I've got my spherical baseball player, and some of them do look spherical to me. And that spherical baseball player is moving from over here on the right to over here on the left. And the initial velocity, we were told, was 6.6 meters per second. And the final velocity, the player comes to rest, that's 0. And two other bits of information. We're told that the mass of the baseball player, and we're told that the slide lasted 3/4 of a second. Okay, so that's the information we're given. So the first thing I did is to figure out the impulse that's given to the player by the frictional force. Then we can find out the frictional force itself that gave that impulse. So here's my calculation for the impulse. The impulse, if you remember, this is This is the impulse. This is the change in momentum of the player. It's the difference between the final momentum and the initial momentum. That's the change in momentum. And then in turn, the initial and final momenta are the mass times the initial and final velocity. So it's this guy and this guy. Now, the final velocity is 0. So that goes away, and it's only the initial momentum that we need to calculate, and that's equal and opposite to the change in momentum. And so I calculate that over here on the right, mass of 85 kilograms times the speed of 6.6 meters per second. And so here's my change in momentum, 561 newton seconds, or kilograms meters per second. I can then, now I've got the impulse that the force gave, I can now go ahead and calculate the force itself with Newton's second law. So in this case, the frictional force, that's what I mean by this guy here, is equal to the rate of change of the momentum, the impulse divided by the elapsed time. And we've calculated the impulse, and we told the elapsed time. And so here's the force, 748 newtons, that was exerted on the sliding player. Now, both of those guys have negative signs, and the negative signs have a meaning that's important. So this guy here and this guy here tell us the direction of the change in momentum and tell us the direction of the force that was exerted on the player. So the player initially was moving from the right to the left, and we called that direction the positive direction. We called the initial velocity a positive velocity. The change in momentum, the impulse, and this force, the frictional force, they're in the opposite direction. They're in the negative direction. So momentum that's towards the right is given to the player to cancel out his momentum towards the left. And the force that's exerted by the ground on the player, that's also towards the right. And those minus signs are telling us that. Okay, let's move on, if I can. And here's another problem involving momentum. So let's see what's happening in this little guy. So this is a problem about calculating impulse and force. Like the last problem was really a problem about calculating impulse and force. But in this one, we got to be a bit more careful about the fact that impulse and force are actually vector quantities. So impulse and force have both magnitudes and directions. Now, in the last problem, everything happened along a straight line. And so plus and minus signs were enough to indicate directions towards the left and the right of the player's momentum, the player's change in momentum, the force acting on the player. In this case, the action is happening in 2 dimensions, vertically and horizontally, and we've got to be more careful about the handling of the impulse because it's a vector, more careful about handling of force because it's a vector. So let's go ahead and do this one. So in this problem, we've got a ball over here. I don't know why I'm coloring it in, but it's kind of fun. And over here, it heads up and towards the right, and it bounces off this wall. and then it heads back over towards the left and up. And so that's the path of the ball. We're told some things about the ball and its initial motion. So we're told that its mass, 2.6 kilograms. We're told that its initial speed, 10 meters per second. And we're told that it's directed at 60 degrees to the wall. So this angle in here, this is 60 degrees. We're also told that when it strikes the wall and bounces off the wall, the speed that it leaves the wall with is the same as the speed that it approached the wall with. And also the angle that it leaves the wall with is the same as the angle that it approached the wall with. So both these angles are 60 degrees. And the question is simple enough. What force acted on the ball when it struck the wall? So look, the ball, just stand back and think of it in sort of conceptually. The ball had some initial momentum that was in a direction that was partly upwards and partly towards the right. So here's the ball's initial momentum. After striking the wall, the ball has some final momentum upstairs here that is upwards and now towards the left. So its momentum has changed. And if its momentum has changed, it was given an impulse. It was given some momentum. There was some momentum transferred to it. And that momentum was transferred to it by the action of the force when it struck the wall. Without the wall, it wouldn't have changed its momentum. It wouldn't have got that impulse. And with that reasoning, we can first figure the impulse that the ball received from the change in its motion, and then figure the force that the ball exerted when it struck the wall. And to figure the force, we're going to use the fact that that force was exerted for 0.2 of a second. Okay, so that's the idea. Let me clear all this junk and we'll do the calculation. And so here's, as I say, I would always make a sketch, always make a drawing, and annotate the sketch with the information I know. And so that's what I did here. I drew the ball heading towards the right and then heading back towards the left. I drew the wall. I drew the information that I was given. Gosh, didn't mean to do that. I wrote down the information I was given, the mass, the speed, the angle. There's also one other piece of information. I forgot to write it down. It's naughty. It was the time for the collision. It was 0.2 seconds roughly. Anyway, that's all the information that we were given in the problem. And now we've got the picture, we can go ahead and start solving the problem. The first thing I'm going to actually do is calculate the momentum, the initial momentum of the ball and the final momentum of the ball. And I'm going to calculate those momenta in terms of the momentum's a vector, the x and y components of the momentum of the ball before and after the collision. So let's go ahead and do that. Okay, so that's what I've done here, I think. Downstairs, somehow I think I've jumped a slide. Let's see if I can go back here. Yeah, this is what I wanted. I think I jumped this slide, sorry. Okay, so what I'm doing here is analyzing the initial momentum. So that's at the bottom of the picture. This is where the ball is starting. And so I call that initial momentum, I called it PI, I for initial. And in terms of the mass and the velocity, is the product of the mass and the velocity. So mass times VI, the initial velocity. And since I know the velocity is 10 meters per second, the mass is 2.6 kilograms, then the product of those, 26 Newton seconds, is the initial momentum. So that is the momentum. I want to figure out, though, to solve this problem, I want to figure out the two components of the momentum, the component that's horizontal and the component that's vertical. And so what I'm going to do is think about this right angle triangle here. The hypotenuse of that triangle is the momentum vector itself. The vertical and horizontal sides of this triangle, they are the X and Y components of the momentum. And if you look, the X component is opposite the 60 degrees angle. The Y component is adjacent to the 60 degrees angle. And so if I want the X component, I want the magnitude of the momentum times sine of 60 degrees, because it's the opposite of the triangle. If I want the Y component, it's the momentum, the magnitude of the momentum times the cosine of 60 degrees, because it's adjacent. And so that's all I did. I was multiplied the total momentum here by the cosine or the sine of 60 degrees. And I get these two results here. Now these signs, there's a sign here, plus sign. Using the sines and cosines and the relationships between the opposites, the adjacents, and the hypotenuse, it didn't really tell me the directions, whether the X component is plus or minus, whether the Y component is plus or minus. For that, I just used this picture here. We were told to think about the direction towards the right as being positive X, told to think about the direction upwards as being positive Y. And so since this momentum vector has a component towards the right, since it has a component up, these are both positive components of momentum. Okay, so now that's the initial momentum. Let's get the final momentum. It's the same procedure, right? It's exactly the same procedure. The final momentum, I called it, not surprisingly, where did it go? Here we are. The final momentum P subscript F for final is, again, from the definition of momentum, just mass times velocity, the final velocity. And it's just the 2.6.2 kilograms times the 10 meters per second. So here's that final momentum. And its magnitude is the same as the initial momentum because the speeds were the same and the masses were the same. Again, if I want the X and Y components of the momentum, Px and Py, I think about this right angle triangle. The hypotenuse of the triangle is the momentum vector itself. The horizontals and verticals are the X and Y components. And if I want the X component, well, it's opposite the 60 degree angle. If I want the Y component, it's adjacent to the 60 degree angle. So that tells me where I use sine and cosine, depending on whether the component is the adjacent or the opposite of the right angle triangle. And that leads me to these two numbers for the components of the momentum. And then for the sines, look at the sines. I put these in by hand again. I just asked myself, well, is the horizontal component of momentum, is it to the left or right? If it's to the right, that's the positive direction. If it's towards the left, which it is here, that's the negative direction. I asked myself, is the Y component of momentum, is it up or is it down? Well, here it's up. That's the positive Y direction, so I put in the plus sign here. And so those are the momentum, those are the momenta before and after the collision, of the ball with the wall in their X and Y component forms. That's what I'm going to work with. Okay, so let me clear that. That's actually most of the work done. Calculate the momentum in X and Y component form. Now we can go on and calculate the force by first calculating the impulse. Okay, so in this slide, I'm just going to calculate the impulse that was given to the ball by the wall. That's the change in momentum that the ball acquired by striking the wall. And over here on the left, all I'm doing is recalling the results from the last slide. The initial X and Y components of the ball, the final X and Y components of the ball. I've just written them out again. Okay, so what's the change in momentum? The change in momentum, I'm going to write down by writing down the change in the X component of momentum and the change in the Y component of momentum. Oops, made a mistake here. So I'm going to answer the question, what is the impulse? What is the change in momentum, by answering the question in X and Y component language. I'm going to write down the change in impulse, the impulse given in the X direction, the impulse given in the Y direction. Impulse, if you remember, will be the difference between the, so here's the impulse, the change in momentum. It's the difference between the final and initial momentum. And here it is also, the change in momentum is the difference between the final momentum and initial momentum. So the impulse given in the X direction is the difference between the initial and final X components of the momentum. And the impulse given in the Y direction is the difference between the initial and final Y components of the momentum. And so that's these two guys, this guy and this guy. And we know the initial and final X components of momenta. We know the initial and final Y components of momenta. So all I got to do is fill them in. And so that's what I did for the X components here. You've got to be careful about the plus and minus signs. That's what I did for the Y components here. And for the X component, if I do the calculation, I get this little guy here. That's the impulse given in the X direction. If I do the same calculation for the Y, I get this little guy here. So importantly, right, and this will make common sense based on the ball bouncing off the wall, originally traveling towards the left and then traveling towards the right, there was a change in the momentum in the X direction. The ball was going towards the X. It is then going towards the, it was going towards the right. It is then going towards the left. So there was a change in the X direction. There was an impulse given in the X direction. And all we've done is quantified that here. It's 45 Newton seconds. But in the Y direction, in the vertical direction, right, the ball originally was going upwards. It continues to go upwards. It was going upwards with a certain momentum in the Y direction. It continues to go upwards with that Y momentum in the vertical direction. And so in the Y direction, there was actually no change in momentum. The entire impulse was given horizontally to the ball. And actually this minus sign here, this even tells us that that momentum that was given towards the ball that was traveling towards the right, that impulse was towards the left. And that's why the ball then started traveling towards the left. Okay, so now we got the impulse. And now it's easy to figure out the force. And that's good because there's only like a minute left, isn't there? And so on this slide, I'm going to just calculate the force, knowing the impulse. So there's only going to be a force in the x direction. That's the first thing, because there was an only non-zero impulse in the x direction. Oh, please no. Okay. I just wasted all my remaining time here. There's only a force in the x direction. I've done it again. Oh gosh. How do I keep doing this? There's only a force in the x direction. There's no force in the y direction, because there was only an impulse in the x direction. There was no impulse in the y direction. To calculate the force, I just take the impulse in the x direction, we figure that out, divided by that elapsed time. We know both those numbers. We end up with that force in the x direction. For the force in the y direction, it's going to be zero, because the impulse in the y direction was zero. And so that's an example, this one in 2 dimensions, of calculating a force given to the ball when it strikes the wall from a momentum perspective, and the fact that forces act to transfer momentum. And that's an important concept, like forces act to transfer energy. So work and impulse are parallel concepts for the energy and the momentum perspectives. Anyway, I'm going to end there.